Okay, we're going to get started in chapter 3 here now. In sections 3.1 through 3.6, we're going to talk about polynomials. Polynomials are really important in math, okay? So it says that a polynomial function of degree n, where n is a whole number, is a function of the form f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 times x to the n minus 2 plus etc. All the way down till we get to the last couple of terms here is a sub 1 times x to the first, or just a sub 1 times x, plus a sub 0, where a sub n minus 1, a sub n minus 2, etc., all the way up to a sub 1 and a sub 0. Those are just real numbers. Okay? Now, a couple of things here. So n is a whole number. A whole number is a non-negative counting number. So 0, 1, 2, 3, those are whole numbers. The degree of any polynomial is all real numbers. Or excuse me, the domain of any polynomial is all real numbers. The degree is just the largest power of x that appears. Okay, we'll do some things with degree here coming up. Now, if f of x is what's called the zero polynomial, the zero polynomial is the only polynomial that has no degree to it. Okay, and we'll look at why that is coming up here. So let's see. Well, in these examples, I want us to determine if the function is a polynomial. If it is a polynomial, we'll state the degree, and if it's not a polynomial, we'll just give a quick verbal explanation as to why it's not. Okay? So what if we had the function f of x equals 3 plus x cubed minus 8x to the fourth? Okay, when we're looking for a polynomial, I need to be adding up a bunch of things here, so that's what I'm doing. Now there's two things that I need to be looking for if I'm in that form. The first thing is every single coefficient in front of x has to be a real number. Okay, so 3, 1, and negative 8, those are real numbers. The second thing is that it says that every single power of x has to be a whole number. Okay, well, 3 and 4 are whole numbers, and so that condition is satisfied. So this would be a polynomial, and the degree is always the highest power of x that we see. Okay, so it's to be a degree 4 polynomial. Okay. How about another example? So what if we had the function g of x equals the square root of x? Is that a polynomial? Well, condition 1, every single value in front of x has to be a real number. 1 is a real number. Okay, and condition 2 says that every single power of x has to be a whole number. Okay, the square root of x, that would be the same thing as x to the 1/2 power. Okay, so x to the 1/2 power, well, 1/2 is not a whole number. So this is not a polynomial. Okay? When it's not a polynomial, we don't say the degree, just it was not a polynomial to begin with. Okay? By the way, if I had any square roots or any other radicals in any function, those are not polynomials. So like if I had 3 plus x to the 1/2 power minus 8x to the fourth, I would not say that this is a polynomial of degree 4. This would not be a polynomial then. Okay, the whole thing is not a polynomial. Here's another example. So what if we had the function h of x equals x squared minus 4 divided by x cubed plus 1? Okay, well, we're not in polynomial forms. We're not in the form where we're adding up a bunch of stuff here. Now, there's going to be several examples where we're not in polynomial form, but we do have a polynomial. Okay, so the next question is, can I get this function into polynomial form? Well, the top and the bottom are both going to factor. Okay, however, you're not going to get anything to cancel in factoring. So the problem is you're still going to have this division bar. Okay, we don't have any division bars going on in this function here, so this is not a polynomial. Okay, now h of x is called a rational function. We'll look at rational functions a lot in section 3.7. Okay, let's try another example. So how about what if k of x equals 0? So I need to check the two conditions. So is every single power of x a whole number? That condition is checked off by default, right? Because 0 times anything is 0. And also, every coefficient has to be a real number. Well, 0 is a real number. Okay. Now this would be a polynomial. Okay, and this is called the zero polynomial function. The zero polynomial is the only function that we say it has no degree to it. Okay, and let me talk about why that is after we look at this next example. So what if we had the function f of x equals 8? Is that a polynomial? Yes. So I need to check the two conditions. So condition number 1, it says that every single power of x is a whole number. Well, I don't have any x's, right? So that condition is checked off by default. Condition 2 says that every single value in front of x is a real number. 8 is a real number. Okay, so that condition is checked off. So this would be a polynomial, and the degree of the polynomial is 0. So 8 is the same thing as 8 times x to the 0 power. Anything to the 0 power is 1. 8 times 1 is 8. Okay, so this would be a degree 0 polynomial. Now, let me come back to this function, k of x equals 0. Now, this is a polynomial. We said that. But this is the only polynomial that has no degree to it. The reason is because 0 is the same thing as 0 times x squared. 0 is the same thing as 0 times x cubed. 0 is the same thing as 0 times x to the 4th. So the degree is something that can't be determined because 0 times anything is 0. Because that happens, we just say that the 0 polynomial is the only polynomial that has no degree. Okay? Every other polynomial will have a degree. So let's try this next one here, g of x. G of x is equal to negative 3x times x plus 2 squared. Okay, is that a polynomial? Well, we're not in polynomial form. And again, there's going to be lots and lots of examples where you're not going to be in polynomial form, but you will have a polynomial. So the question next, it would be, can I write this function in polynomial form? Can I write it in the form where I'm adding up a bunch of terms there? And yeah, so x plus 2 squared, that's the same thing as x plus 2 times x plus 2. When I FOIL that out, that'd be x squared plus 4x plus 4. I'm multiplying that by negative 3x. So negative 3x times x squared would be negative 3x cubed. Negative 3x times 4x would be negative 12x squared. And negative 3x times 4 would be negative 12x. Okay, so is g a polynomial? Yeah, because the two conditions would be satisfied. So I'm in the form where I'm adding up a bunch of terms here. And so Is every single power of x a whole number? Yes. 3, 2, and 1, those are whole numbers. And is every single value in front of x a real number? Yes. So -3, -12, and -12, those are examples of real numbers. So that condition is satisfied. Okay, this would be a polynomial, and the degree of the polynomial is 3. The degree is always the highest power of x that we see there. Okay? Let's try another one. So h of x equals the absolute value of x plus 2. Is that a polynomial? No. So in the definition, we don't have anything involving absolute value bars here. So any function involving absolute value bars, those are not going to be polynomials. Okay? All right. Now, if f is a polynomial function of degree n, so we're in this form, and the degree is n, then f has at most n minus 1 turning points on it. There are at most n x-intercepts. So a turning point is where you change from increasing to decreasing or decreasing to increasing. Let's see, here's an example. So f of x equal 3x to the 4th minus 4x cubed minus 12x squared plus 3. First of all, that would be a polynomial, right? Because I'm in polynomial form. I'm adding up a bunch of things there. And the two conditions would be satisfied. So condition 1 says that every single power of x is a whole number. 4, 3, 2, those are whole numbers. And condition 2 says that every single value in front of x is a real number. Well, 3, -4, -12, and 3, those are real numbers. Okay, so we do have a polynomial. Now, if we wanted to know at most how many turning points there would be on this curve, like if I were to draw this curve, there would be at most 3 turning points. Now, the words at most, that's key, because we're not saying that the function has 3 turning points. You know, like this function might only have 2 turning points, or 1 turning point. Or it's not going to have no turning points, because otherwise you'd have a line, right? And I don't have a line, but there's just not more than 3 turning points. Okay, there would be at most 4 x-intercepts. So the degree is 4. And again, you know, the words at most, that's key. So there might be, you know, only 2 x-intercepts, or there might be no x-intercepts. Okay, there's just not going to be more than 4 x-intercepts. One of the things that we're going to have to know here is the end behavior of a function. Okay, so if n is an even number, and that's greater than or equal to 2, and a sub n, the leading term, is a positive, then what that means is that the graph is going to open up on both ends. I don't know what's happening in the middle. You know, I might take 2 turns or 3 turns or 48 turns or whatever. All I know is that it's going to open up on both ends. If n is greater than or equal to 2, and that's an even number, and a sub n, the leading term, is a negative, well, think transformations. So I'm going to flip the graph upside down, and you're going to open downward on both ends there. If n is greater than or equal to 3, and that's an odd number, and a sub n is a positive number, then what's going to happen there is you're going to open upward on the right and downward on the left. Again, I don't know how many turns there's going to be. If there's 3 turns or 48 turns or whatever, I don't care about that. I just know what's going to happen on both ends. Okay, and then in this last situation, suppose that I have a degree that's an odd number, and and n is greater than or equal to 3, and a sub n, the leading term, is a negative. Well, think transformations. So I'm going to flip this graph upside down, and I'm going to open upward on the left and downward on the right. Okay, so that's very helpful. You know, if I want to do anything with graphing, like I can know how many turns there would be. And by the way, you know, this function, this is going to open upward on both ends. So n is 4. 4 is an even number, and a sub n is 3. Okay, so I have no idea what this curve looks like, but I know what's happening on both ends. I'm going to open upward on both ends. Okay, let's take a look at these problems next. So, well, here's the same function that we were just given right here. So 3x to the fourth minus 4x cubed minus 12x squared plus 3. Okay, if I were to draw that graph or use my calculator, here's a rough sketch of what that graph looks like. Okay, so I know that there's at most 3 turns. There is at most 4 x-intercepts. Here there would be exactly 4 x-intercepts. 1, 2, 3, 4. And I know I'm going to open upward on both ends, right? Because n is a positive, n is an even number, and I've got a positive value for a sub n. Okay, so I'm going to open upward on both ends. Let's try these 2 examples next. So I'll give you a function, and let's just describe what's happening, or how many turns at most there would be, and then what's happening at the 2 ends of the curve. So what if I have g of x equals x squared minus 4x cubed? Well, there's going to be, so this is a degree 3 polynomial, and that means that there's going to be at most 2 turning points, and there's a negative 4 in front of x cubed, right? So what's going to happen on both ends is negative 4 is, looks like I'm going to open upward on the left and downward on the right. Opens up on the left and down on the right. Okay. Let's try this example. So what if I had the function h of x equals 5x cubed minus x? How many turning points are there at most? And then what's happening on both ends? Well, I've got a degree 3 polynomial. And so there's going to be at most 2 turns on this curve. And what's happening on both ends is that I'm going to be falling downward on the left and opening upward on the right. So very similar to y equals x cubed. So n is 3, right? We said that. We had degree 3 polynomial. And a sub n is 5. That's a positive number. So I know I'm going to be opening upward on the right and downward on the left. Okay. Now that's important when it comes to graphing, you know, because I don't want to be stuck point plotting. Like I'd like to know more sophisticated methods for graphing curves. Okay, and so these are helpful to me when it comes to graphing there. All right, in this section, be sure to look at the homework, which is on page 175, and we'll get into 3.2 on the next section there.